Hello, my name is Viktor. I'm a PhD student at Karazin National University. Today, I'm going to present results of the attempt of simplifying a model of a distributed system for statistical estimating of CAP constraints violation. Now I give a brief overview of what CAP constraints are, also known as Brewer conjecture. Originally, it stated that it is impossible to achieve all three desired properties while building a distributed web service. Those properties are consistency, availability, and partition tolerance. In practice, it means that the one cannot guarantee consistency and availability all the time, meaning that no matter what, the data will be always provided upon request and be always up to date. In practice, the statement does not give enough clue about system behavior, because lack of guarantee doesn't mean that the system is always unable to provide up-to-date data. As Martin Kleppmann in his paper Critique of CAP Theorem told that CAP theorem cannot be an appropriate tool for reasoning about distributed systems, and new framework development is required. Later, he proposed a delay sensitivity framework. That's an alternative way to the challenges I will be talking about today. Relatively recently, a new approach was proposed for specifying probabilistic characteristics for CAP properties measurement. The initial proposition was done in the paper Distributed Data Stores towards Probabilistic Approach for Estimation of Reliability. The main idea is to reason about the quality of distributed data store using probabilistic metrics for CAP properties. Later, I will provide the metric definition for partition tolerance property. The rest of the metrics can be found in the original paper. As part of further research actions, the authors describe the following steps. Simulate the model of distributed data store and study different mechanisms to estimate a degree of ensuring each guarantee by applying specified metrics. This presentation is focused on modeling distributed data store and estimating statistical violation for partition tolerance property from Brewer's conjectures. Now let me show a distributed data store model used in the work. The model consists of 5 attributes: set of nodes, set of links between nodes, mapping which associates every link with 2 nodes, set of stored data units, mapping of data units and nodes the unit stored at. At the initialization moment, when nodes are established, each node has the probabilistic distribution of recovery time and time of failure. In a distributed system, links that bind nodes may also fail. But during this particular research, it is assumed that links are always reliable. To be able to calculate the probability of partition tolerance fulfillment, we need to take into account these distributions in the research. The purpose of the estimation is further simplification of a distributed data store model by substituting nodes probabilistic distribution with one average distribution for recovery time and time for failure, and estimating changing in system behavior by using metric for the partition tolerance property. The metric used to estimate partition tolerance is a random variable zeta that represents 2 possible events. Zeta is equal to 0 means that there exists a data unit which is not reachable by some node from the subset of alive nodes. And zeta is equal to 1 means that all data units are reachable from any alive nodes. It is assumed that the distribution of fail and recovery time for every node obeys Poisson distribution. As we can treat time in our experiments as discrete quantity, events, failure, and recovery as a series of events with the known average time, but the exact time is random. Saying that some node has a different distribution compared with some other node, it is understood as both of them are having Poisson distribution, but parameters of Poisson distributions are different. When data for a model of distributed data store with every node having a different probabilistic distribution of fail and recovery time is not statistically different from the model with node having the same distribution. The empirical results to the question will be presented together with the way the results were obtained. In order to collect data for statistical estimation, the model of distributed data store was simulated and the state of the system was constantly recorded. By experiment, I mean simulation of distributed data store during some period of time. Time in the experiment is treated as discrete quantity. Series of many experiments were conducted and now presented only the most notable ones. Before every experiment, the list of the next steps must be executed. Generation of graph, which corresponds to nodes and links of a distributed data store. Generation of parameters for Poisson distribution of fail and recovery time for every node from the generated earlier graph for a system having different parameters of distribution referred as original. Generation of parameters for Poisson distribution of fail and recovery time for every node from the generated earlier graph for a system having common parameters of distribution, referred as ideal, and define discrete time series T. To generate a graph, Watts-Strogatz model was used. The model produces a random graph with small world properties that well represent real-world systems, especially distributed across different geographical locations. The next properties of Watts-Strogatz model were used as the input parameters for every experiment. Probability of rewiring, which influence clustering coefficient of graph, and degree which influence connectivity of the graph. The next steps are taken to define parameters for both systems, as original and as ideal. Define expected value of fail and expected value for recovery time for as ideal. Mentioned values are the input parameters of an experiment. For every node from as original, calculate random values, deviation for recovery time and deviation for time to fail, based on normal distribution shown on the slide. And then it is needed to define expected values for as original. The way of definition is shown on the slide as well. During experiment execution for every t, the respective value for zeta is recorded for both systems as ideal and as original. The process is repeated for randomly generated graphs. Values for random variable zeta are aggregated per number of times the system had a respected value and stored in buckets. Buckets are needed for precision and to eliminate noises for the statistical relationship test. For statistical relationship test, Pearson test was used with p-value more than 0.05. In total, more than 5,000 different systems were generated and experiments conducted. Graphics and Pearson test results along with the input parameters can be seen on a slide. Results for the next set of the experiments. It is possible to conclude that bigger expected value of time to fail in comparison to the expected value of time to recovery highly contributes to Pearson test results. During this set of experiments, small deviation value was used. As a conclusion, I present a list of parameters that highly affect the Pearson test outcome. Ratio of expected values of time of failure and time of recovery. Average deviation and graph clustering. Bucket size, which can be treated as a precision of system behavior. After understanding the relation of every parameter to the end result, the next proportion can be defined. The next steps will be focusing on improving current relation by specifying coefficients for parameters, making their influence more explicit. And this relation can be used for studying next metrics defined in distributed data stores towards probabilistic approach for estimation of reliability paper, while taking into account that system by itself can be simplified from partition tolerance perspective. Thank you for the attention.